moving on. 4.4, here we go. So let's start getting into graphing rational functions. Okay. That's really the main objective of the section. Can you graph a rational function, and maybe can you do some word problems? Really what we're going to do, we're not really learning how to do anything new in this section. We're just going to combine a bunch of information we've already learned and see how to use it to draw graphs. So let's just jump right into an example. The first step you want to do is factor everything. The goal of factoring the numerator and factoring the denominator is to make sure it's in lowest terms and to find the domain. So the numerator is already factored. It's just x minus 1. There's nothing to do. But the denominator factors as a difference of 2 squares. It's already in lowest terms. There's no factors to cancel off. So the domain is just everything except plus or minus 3, because those would have made the denominator 0. Next, write it in the lowest terms. If there's anything to cancel, now you do it. Because remember, as mentioned in an earlier video, when you do this cancellation, you might lose information about the domain, but that's the only information you could lose. So as long as you find out your domain before you do any cancellation, you're fine. So first, find the domain and then cancel it. This one didn't have anything to cancel off, so we're already done here. The next step in the procedure is intercepts, x-intercepts and y-intercepts. And remember that with x-intercepts, they have a multiplicity attached to them. Even multiplicity means the graph touches the axis. Odd multiplicity means it goes through the axis. I accidentally went 2 slides ahead, so let's just talk through this whole thing. So 0 is in the domain, which means I can plug it in, so it has an intercept. And when you plug in 0, you get out 1/9. The function was just x minus 1 over x squared minus 9. Sorry. So yes, 0 can be plugged in, and you get out 1/9. The x-intercepts are found by setting y equals to 0. But notice, if I set a fraction equal to 0, if I just multiply the denominator, I really just get that I want the numerator to equal 0. So finding roots of a rational function, as long as it's written just as one polynomial over another and there's not any other crazy stuff going on, you really just have to solve where is the numerator 0. And this only has a single 0 at x equals 1. So the only x-intercept is at 1, 0. It's also got multiplicity 1 because it appeared just as x minus 1 to the first, not x minus 1 squared or anything like that. So the multiplicity is odd, so the graph is going to cross at this root. So we put that down as another bit of information. Okay, the next step is find vertical asymptotes. Spoiler alert, step 5 is going to be horizontal asymptotes or oblique asymptotes. Okay, so our graph, again, was x minus 1 over x squared minus 9. So to find vertical asymptotes, now that it's in reduced terms, we just find roots of the denominator, which we already found in a previous step. They were x equals 3 and minus 3, so those are going to be vertical asymptotes. Okay. Also, there's a bit of analysis given in this slide that wasn't mentioned on an earlier one. I'm going to clear out some space here. So imagine you have something over x minus k to an odd power. So I have a vertical asymptote at x equals k. What does it do on opposite sides? Okay, so there's something on the numerator, and there might be other stuff in the denominator. But since I'm in lowest terms, the numerator is not 0 at x equals k. So this bit here and this bit here are not 0 at x equals k, which means they're either positive or they're negative, but they're just some number. So if I plug in a value of x really, really close to k, it's either just a tiny bit bigger or just a tiny bit smaller. Then take a look at this bit right here. If x is a tiny bit bigger than k, I end up with a very, very small but positive number. I raise that to an odd power, and that's positive. But if x is just a little bit lower than k, then this is going to be negative, and a negative number to an odd power is negative. In other words, depending on whether x is just a little bit smaller or bigger, just a bit smaller or just a bit bigger of k causes the function to change from positive to negative. Because this bit here, x minus k to an odd power, is going to change between positive and negative, and this stuff is just very, very close to some number. It's not changing positive to negative. What's important is that this is changing where x is k, this goes across 0. It changes positive to negative. If this numerator was 10 and I change x a little bit, it's still going to be close to 10, but that's still going to be positive. If this was negative 8 and I change it a little bit, it's going to be close to negative 8, but still negative. The only thing that actually changes is close to 0. So if x is close to k, then this can change from positive to negative or vice versa. So if you have an odd multiplicity root, your vertical asymptote has changing behavior, which means it draws either like this, positive on one side and negative on the other, or like this, negative on one side and positive on the other. But it does opposite things on both sides. Conversely, if you have something over x minus k to an even power, an even multiplicity root, then if x is very close to k, x minus k might be positive or negative, but to an even power, it's positive on both sides. So here, your asymptote does the same thing on both sides. In other words, it could do this, or it could do this. They might both go up, they might both go down, but they both do the same thing. So when you have a root of the denominator of even multiplicity, the vertical asymptote will have the same direction on both sides. When your denominator has a root of odd multiplicity, the vertical asymptote will do different things on both sides. So in this example, again, I'll copy the function back up here. It was x minus 1 over x squared minus 9, which has been factored as x minus 1 over x plus 3x minus 3. Both of these roots are of multiplicity 1 in the denominator, which means the vertical asymptotes will have opposite directions on each side. I don't know which side goes up and which side goes down, but I know they do opposites. Step 5, find the horizontal asymptote. And again, the function is x minus 1 over x squared minus 9. Well, since the degree of the numerator is smaller than the degree of the denominator, y equals 0 is a horizontal asymptote. Okay. You should ask, does it ever intercept the horizontal asymptote? Now that I know y equals 1 is the horizontal asymptote, will this ever intersect it? This, in this particular problem, becomes, is x minus 1 ever equal to x squared minus 9? In other words, is x squared minus x minus 8 ever equal to 0? I just moved everything over to one side. Okay. Then I would use the quadratic formula. X would be equal to 1 plus or minus b squared minus 4ac is going to be 33 over 2. So there are, in fact, two values where I do actually touch my vertical asymptote. Sorry, not vertical, my horizontal asymptote. This is not actually given as a step in the book's way of doing it, but I think it's a useful thing to do. Now that I know what the horizontal asymptote is, does it ever actually intercept it? Oh, my mistake, I'm sorry. 1 was not the horizontal asymptote, 0 was, so that's all wrong. But in general, whatever the horizontal asymptote is, you should try to ask, does it ever intersect it? Okay, next, use the zeros of the numerator and denominator to split the domain into intervals. Zeros of the denominator give you places where the domain, where it's not in the domain. Zeros of the numerator give you where the function is 0. in between such places, the function has to always be positive or always be negative. So for example, if here's my number line, okay, and again, here's our function. It's x minus 1 over x squared minus 9. I know that at x equals minus 3, this is not in the domain. This is a vertical asymptote. X equals 3 and minus 3. This is also a vertical asymptote. It's not in the domain. And x equals 1 is a root. So what does the function do in between such things? I found all of the vertical asymptotes and all of the roots. So the graph does not have any roots in between -3 and 1, but it exists because there are no other vertical asymptotes. So in between -3 and 1, it's either always positive or always negative. Similarly, once I have this root here, to the next vertical asymptote, it's either always positive or always negative, but I don't necessarily know which one. What I do know, however, is that since this root is of odd multiplicity, that the graph does go through the axis. So if it was positive to the left, it will be negative to the right, and vice versa. I still don't know which one it is, but I know it changes. And then to the left of this vertical asymptote, again, I'm either always positive or always negative. And to the right, I'm either always positive or always negative. And then I could just ask, how will I determine which one it is? Some test points will be quite handy. Whoops, I should clear off my pen marks. So yeah, just divide the real number line into intervals according to the roots of the function and the vertical asymptotes. And we get the following 4 things. Left of a vertical asymptote to root, root to vertical asymptote, and right of vertical asymptote. And then just using some test values. Okay. What is a test value to the left of -3? How about -4? In between -3 and 1? Well, 0 is a good choice. In between 1 and 3? 2. 3 and infinity? How about 4? These don't have to be whole numbers. Okay. If one of the roots was at 1 and then there was a root at 2, you'd have to find a number in between 1 and 2. How about 1.5? Okay. There's no reason these have to be whole numbers. It's convenient when they are, which is why we're choosing them that way, because we have the option. But if there aren't any whole numbers in between 2 consecutive vertical asymptotes, for example, pick a non-whole number and just deal with it. Okay, so if you plug these into the function, so r of x was x minus 1 over x squared minus 9, just plug these in and you'll get out these r values, which means since it was negative here and it did the same thing on this whole interval, it must be negative on that entire region. Similar reasoning, since it's positive here, it's positive on that entire interval. Negative means negative, positive means positive. Okay. And we can combine all of that information. So we have our vertical asymptotes at 3 and -3. We have our horizontal asymptote of y equals 0. Those are the pink lines. And then we can summarize everything. So we know the horizontal asymptote was y equals 0. So the graph has to get very close to y equals 0, which means it could do this or it could do that. But since we knew the graph was negative to the left of this vertical asymptote, it has to do this. Similarly, since we knew the graph was positive to the right of the last vertical asymptote, it has to come in from above on this side. Okay, so we're using the information of where the graph was positive and negative combined with where the horizontal asymptote is to get some good information here. Similarly, because the graph was positive here and negative here, because I have a vertical asymptote, if the graph is positive, I have to go up like this. I couldn't possibly have this direction, because then the graph would have to be negative, and it isn't. Okay, and similarly, since the graph was negative here, and here's a vertical asymptote, that has to go down. Since it was positive on this side, it has to go up on that side of the vertical asymptote. Also, remember our vertical asymptotes were of odd multiplicity, meaning we have different directions on both sides. So once we concluded that the left of this vertical asymptote was going down, then this one would have to go up. And since we know that this side goes up, we can actually conclude that this side must go down. Okay. So we've already done this argument. Great. So since this has to go down on this side, we just follow it that way. Here was our root. So we connect this vertical and this vertical asymptote going through the intercept and the root involved crossing the axis, so now we go down negative. And then we knew we had this going up and this flattening out in this direction, and we just sort of join them up as we can. Okay, so whoops. So there is a nice graph combining all the information in this example. Okay, so we'll stop this one here, but come back and we'll keep doing examples.